With mutating traversals, we can add or remove vertices, edges, or properties from the graph itself. There is a separate graph API to do this directly, and that API is more efficient with DSE graph. So if you have a lot of mutating to do, mutating traversals might not be the kind that you would like. But there are some kinds of mutations that you need to do in terms of a traversal. You have previously learned that we have 5 ways to insert data into DSE graph. Mutating traversals are one of those 5 ways. The mutating traversal gives you the ability to add or remove vertices, edges, or properties into the graph. This is kind of like walking around the data to find a set of vertices or edges that you would like to mutate. We have 4 new steps to get these mutations done. There is addV, that simply adds a vertex. And at the time of adding a vertex, we can give it a label. We have addE that adds an edge. Now, to add an edge, we also need to tell the vertices which that edge is connecting. So this will create a newly labeled edge, but we will also need to use a modulator to say where the edge is coming from and where it is going to. There's also the property step that lets us add a new property to a vertex or to an edge. Finally, there's drop, and we use drop to remove a vertex, an edge, or a property. Dropping a property just removes the key and value from the vertex or edge. When you drop an edge, it just removes that object from the graph. But when you drop a vertex, it will also drop all of the incident edges of that vertex. So that drop might do a little bit more work than you expect. But when we think about property graph structure, that extra work when dropping a vertex is necessary to ensure that we have the correct graph structure after a vertex has been removed. As we mentioned, adding an edge requires that we come from a vertex or go to a vertex. The from and to modulators do that. When we use the addE step, we want to use that on a vertex or vertices in the traversal. We have to then specify where that edge is going to come from or where that edge will go to. Of course, however, we use the step from or to establish the direction of the edge. Also, we can come from or to a labeled step, where that labeled step can be one or more vertices. And we can also go from or to a new traversal so that we can explicitly specify that traversal that generates the vertices that the edge should go to or come from. The step modulators can take 2 different types of parameters. First, you can give it a previously defined step label that can be one or more vertices. Next, you can also write a traversal to find or walk to a set of vertices to connect. As always, for the examples, let's remind ourselves of the killer video movie schema. We have movies that belong to genres, and we have users who rate the movies where users also know each other. We have other people in our graph that have acted, directed, composed, or other types of actions with the movie. So let's see what we can do to mutate our graph according to this schema. Let's say that we would like to go to all of the Tom Hanks movies in our schema, compute the average ratings, and store those ratings on the movie vertices themselves. Let's take a look at the code. We will first find the Tom Hanks vertex. That is g.v has person name Tom Hanks. From there, we will traverse the incoming actor edges. That is, we are going to take us to all of the movie vertices that have had Tom Hanks as an actor. From there, we are going to mutate those vertices by creating a new property. From there, we are going to mutate those vertices by creating a new property. That is the property mutating step that you see on the second line. We are going to create a property called average. The value of this property is going to be equal to the third line. Here, we have an anonymous traversal, and we need a reality check at this point to know where we are in the stream and within the graph schema. At this point, we're at the movie vertices. Next, we need to traverse to the incoming edges with the rated label and calculate the mean of the rating values on those edges. That is the remaining part of the traversal, which we see on the second line. It computes the average rating for the Tom Hanks movies. At this point, the mutation is done. We have added the average property to the Tom Hanks movie vertices. The last line is just providing the output that we would like to see. It is getting the average property and the title property and emitting those in the list that you see. As you see in the results, Castaway was rated pretty highly, about a 7.1. Then you have other movies like The Da Vinci Code, Sleepless in Seattle, and You've Got Mail. For our next example, how about we add a new genre into the graph? Say a genre for biographies. This is a pretty simple mutating traversal. We're going to add a vertex called genre, and we're going to give it a couple of new properties. We're going to give it a new ID and then a name, which is biography. Then the value map prints out this information to see the vertex and all of its properties as a map. This is just a new way to add a vertex into the graph. Currently, it's an isolate vertex or a disconnected vertex, but it is in our graph. Let's see what we can do with it. Now, Bridge of Spies is arguably a biopic of attorney James Donathan. So let's see if we can add an edge from the new biography genre vertex that we have created. And let's walk through the code. We begin by adding the movie itself. So we add a new vertex with the movie label and fill it up with properties. We give it a movie ID, the title Bridge of Spies, its year, duration, and country of origin. And there we have it. Then we are going to label this vertex with the as step and give it the label new so that we can refer to it later on in the traversal. Next, we're going to add an edge. This edge will have the actor label. There is more we could say about this film, but we only want to add the actor edge over to the person vertex with the name Tom Hanks. So we addE actor to the Tom Hanks person vertex. Then we have the line that says select new. This effectively will go back into the traversal to the vertex that we labeled new. So going forward, after the select new line, the stream will see that vertex. We will add another edge from that vertex to connect the Bridge of Spies movie to the newly created genre vertex, biography. This is the last two lines of this mutation. So we created a movie, gave it some properties, associated the movie with an actor, and associated it with a genre. In this previous example, we added two edges, but we added them explicitly. This time, we're going to use a traversal to add edges to a collection of vertices. We begin, again, by getting the Tom Hanks person vertex, and we label it Tom. On the second line, we traverse the incoming actor edge. This gets us back to all of the movies in which Tom Hanks has been an actor. From there, we traverse the outgoing actor edge to get all of the other actors who have acted in movies with Tom Hanks. So this is potentially now a large set of people vertices at the end of the second line. Then we will put a constraint saying that we don't want these people to be equal to Tom. Essentially, what we did was we found Tom Hanks, went to his movies, and went back to all of the actors who were also in Tom's movies. And when we do this, of course, we could find Tom more than once. However, we don't want him in this set. Also, we don't want any duplicates, like in the case of Meg Ryan, who appeared in Sleepless in Seattle and You've Got Mail. So here, we use the dedupe step to remove the multiple versions of the same actor from this set of people. Now, in this line, we're going to actually mutate the graph. Coming into it, we have a collection of vertices, and we are going to add an edge from all of these vertices with the label nose. That edge will be coming from the Tom vertex, which we labeled in the first line. We have now created many edges from all of the actors who have been in movies with Tom Hanks, and we are asserting that they know Tom. The purpose of the last part of this traversal is just for display. At this point in the stream, we are on edges, but we need to traverse to the people and then look at their names. And in the output here, we can see that we have found Chris Noth. And in the output here, you can see that we have Chris Noth, David Allen Brooks, and Mr. Blake. In this next example, we are going to play with adding edges and removing them. What we are going to do here is that we're going to turn all of the actor edges into actedin edges in the reverse direction. In our schema, we have movies that have actors, which are people. People don't have any notion of having acted in a specific movie. So for this example, we would like to go to the Tom Hanks movies, remove the actor edges, and add in actedin edges in the reverse direction. We will start again on the first line, finding the Tom Hanks vertex and labeling it as Tom. We do this so that we are able to use it later on in the traversal. Next, we go back along the incoming actor edges and we label those vertices as movie. That will be all of the movies that Tom Hanks acted in. From these movies, we are going to add an edge called actedin that comes from Tom. So the directionality here is opposite of the original direction for the actor edges of our schema. The Tom vertex has an edge that points to his films and says that Tom acted in these films. At the end of the third line, what we have in the traversal are edges. The mutation is complete, but it's going to pass those edges on into the next step. From those edges, we're going to walk to the outgoing vertex, which will happen to be the Tom person. Then we will select the incoming actor edges and drop them. So essentially, the normal actor edges that we have in the schema have been reversed and are now called actedin. So let's take a look at some of the results. The second traversal on this slide shows that we get to the Tom Hanks vertex and we want to count how many incoming actor edges there are. Sure enough, there are 0 because we removed them. In the third traversal, we will go to the Tom Hanks vertex and we will count the outgoing actedin edges and we see 10, which reflects the dataset that we have in our sample graph schema. So essentially, in this example, we have removed the actor edges, replaced them with actedin edges, but now they're in the reverse direction. In this next example, let's combine a mutating traversal with a declarative traversal. We previously covered declarative traversals in another video, but let's still take a moment to see what's going on. We begin again by finding the Tom Hanks person vertex. Then, the next 2 lines are our declarative traversal. That's the match step. The match step contains 2 patterns. Both patterns start off with an anonymous traversal. Also, both patterns contain variables, Tom, M, and X. In these patterns, we are simply declaring the relationships. that these things have, but we are not specifically telling the traversers how to find them. So Tom, whatever it is, has an incoming actor edge to a thing called M. In the second pattern, M has an outgoing actor edge to a thing called X. Now, those assertions will match a certain part of our graph, and we will later find out what they are. Now, on the next line, we are going to say that the X variable cannot be equal to the Tom variable. And that is an additional constraint, where X is not equal to Tom if you think about it. If you go from Tom to the movies he has acted in, we are going to say that we don't care about the times that Tom has acted in the same movies with Tom. We only want to know when Tom acted in movies with other people. So we say that X cannot be equal to Tom. Next, we remove the duplicate actors. That's when we get to our mutating traversal. At the end of dedupe X, we have a collection of vertices. From those vertices, we will add edges with the nose label. Those edges will come from the Tom vertex and go to the vertices in X. And those edges will all go to the set of people identified from our match step earlier on. And lastly, let's go back to the incoming vertices, pick out the names, and see which actors that we have. We see Chris Noth, David Allen Brooks, and Mr. Blake. Now, this last example was the same as the previous example. It just does it in a slightly different way. In this example, we combined declarative traversals with the mutating traversal. I hope these examples have given you some more information on how to add or delete data within your graph. So enjoy the next exercise, and we'll be right here.